All right, well, welcome back, everybody. In this video, we are going to talk about the dot product, which is a way to quote unquote multiply two vectors together. In other words, to take two different vectors or the same vector as input and to combine them in some meaningful way. Now, this is an example of a vector operation, and we've already seen some vector operations, such as vector addition, where we add two vectors together, giving us another vector, or scalar multiplication, where we take a vector and multiply it with a scalar. So the dot product is something a little bit different. We're going to combine two vectors together, but the end result is not going to be a vector. So when we calculate this dot product, the resulting answer is a scalar number. And the number that we get will actually encode a little bit of geometric information in a pretty interesting way. And when I say that we multiply these two vectors together, I should say these are two vectors in the same n-dimensional space, but they could be any n-dimensional space. So let's call them v and w. And these are going to be vectors in our n, so n-dimensional space. And then we're going to multiply them together using this dot product. And when we multiply them together, what we will do is we will write that as v dot w. And when I read this out loud, I'll actually read it out loud as v dot w, as opposed to v times w or something like that. I'll read it as v dot w. So how do we go about doing this? Well, if these are n-dimensional vectors, so we've got our vector v is going to be this vector with all these different components. So let's say it's v1, v2, up to vn. So n components because it's n-dimensional. And then we've got w is this other n-dimensional vector. So it's got w1, w2, up to wn. Then when we multiply them together, we take v dot w. We're going to do this as follows. First, we are going to take the first component of each vector. So that's v1 and w1. And we're going to multiply those together to get v1 times w1. So each of those are just numbers. Remember, we can multiply those together using good old-fashioned multiplication. And so that's v1, w1. Then we're going to do the next two components. So that's v2, w2. And we're going to get v2, w2. And we're going to add these on. So we're going to take our first product, v1, w1, plus v2, w2, plus, and you can sort of see where this is going, we would do plus v3, w3, plus v4, w4 if necessary, dot, 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 all the way up to the final product, which is vn, wn. And notice, because each of these were individual scalar numbers, we multiplied them together and we added them all up, the end result is a scalar. To see an explicit example of this, let's keep it pretty simple. I don't know, let's say these are three-dimensional vectors. So v is the vector 1, 0, -2. And w is the vector 3, 1, 4. Then when we combine these together in this dot product way, we're going to get v dot w equals, and then the first components multiply together, so that's 1 times 3. The second components combine together, so that's 0 times 1. And the third components combine together, so that's -2 times 4. And then the dust can settle. Let's hash this out. This is going to be 3 plus 0 minus 8. And so the end result is going to be -5 in this case. The dot product of this v and this w are -5. And that's the dot product. It can work as long as you can see our two vectors are of the same dimension. We can always make sense of this and get a number, a scalar, as an answer. Now, what I'm claiming is that that scalar number encodes some important geometric information. So this -5 is actually telling us something about the relative position geometrically of V and W in this three-dimensional space. And we might not see that right now, and it might take us a little while to develop that geometric information. But I do want to conclude this video by talking about one really nice way in which the dot product encodes geometric information, and that is through the idea of length. Whoops, there we go. So when we talk about a vector's length, the length of this vector is just the length of the corresponding arrow in n-dimensional space. And so let's take a look at what is happening with that. So if we were to, for example, look at a vector in R2, let's specifically, let's look at the vector 3, 4. There's a vector in R2. I'll just draw a quick set of axes here. Okay. And then this vector, of course, goes 3 units over and 4 units up. So if I did that right, 3, 4 is the vector drawn in standard position. That's sort of pointing right up here. We'll pretend that's a good picture and that's a straight arrow and all of that. Okay, so this is our vector 3, 4. And what I'm going to claim is that the length of 3, 4 is the length of that arrow, like the physical length of that arrow. And we can calculate that using the dot product in this manner described up here. I think the way we calculate it is actually given over here. We calculate the length by taking that vector dotted with itself and then square rooting it. Another way that we can write the formula is given to the left, in which we say that the length of the vector squared is equal to the vector dotted with itself. These two formulas, so this formula and this formula, are just equivalent to each other. But how will we actually see this in practice? So to calculate the length of the vector 3, 4, we would say, well, to calculate v, we're going to need to take the square root of v dotted with itself. And so that means we'll have to take the v dotted with itself first. And so that's going to be 3, 4 dotted with 3, 4. Using our work from above, that's just going to be 3 times 3, right? The first component times itself plus the second component times itself. And that's just going to be 9 plus 16. And so that's going to be 25. V dot v is 25. And then we can conclude that the length of v, which is the square root of v dot v, is just going to be the square root of 25. So it's just going to be 5. Cool. Okay. We can also see this, though, and we can make sense of this formula by recognizing that what we see here, right? This was the vector 3, 4. That means that it moves 3 units in the x direction. So we counted off earlier, 1, 2, 3. But let me physically draw that line and say that's a line of length 3. And then 4 units up in the y direction. So 1, 2, 3, 4. We'll draw that. And what we see is that this is not just a vector, but this is the hypotenuse of a right triangle, whose one side length is 3 and whose other side length is 4, right? And so, of course, the length of this side, this hypotenuse length, is going to be 5 because it is a 3, 4, 5 right triangle. And just very briefly, like this helps justify this formula for length of a vector. We'll see that this is always true in the two-dimensional case. This kind of picture will always be true. And in fact, a similar thing will always be true in the n-dimensional case as well. So if we were to draw an arbitrary vector here, just making this up, say it's like that. And so let's say that this is the vector W, which is given as W1, W2. What that means is that we moved W1 units in the x direction. So this base length here is a length W1. And then we move W2 units in the y direction. So this length here is length W2. And what that means is that this final length, this hypotenuse length, which is of course the length of W, the length of the vector, given by the Pythagorean theorem, is going to be the square root of W1 squared plus W2 squared, which is exactly what we get when we calculate W dotted with W. All right, so this is one way in which we can use the dot product to interpret geometric information, specifically length. And we'll see that there are other ways that we can use the dot product going forward. So thank you so much for watching. See you all next time.